All right, I think I got everything. Let me get rid of these substandard markers. Are these good? Eh. Is this my juice? No, this is the... Man, I lost my juice. I don't know where I put it. Now I've got this other... That thing leaks like a lot. Every time I use it, I get my hands covered with the board cleaner. I've got to find my... you know, my original bottle.
Put an air tag on your bottle.
an air tag on my bottle, yes. That seems like a completely legitimate use of an air tag. I like that. It's not bad. All right, well, I will begin with a word of prayer. Heavenly Father, we thank you for this day again. I thank you for this class and this opportunity we have just to meet, study your creation, and just pray that we'd learn a little bit more about manifolds today, and that we glorify you what we do, Lord. In your name I pray, Lord Jesus. Amen. Oh, hey, Jeff.
We were just talking.
That's right. I have plans for you.
I know the plans I have for you, Doctor. Plans to go.
Vector fields. All right, yeah, let's go.
Exactly.
All right. So I am, I guess, skipping past something I really, really wanted to talk about, which maybe we'll circle back to eventually. I don't know. So what I was going to say is the thing I haven't talked about yet in Chapter 7 was the representations of Lie groups. So a representation of a Lie group is essentially a subset of matrices which act on a vector space in a natural way. So it's also called a matrix realization of a Lie group. And so interesting formulas at the end of Chapter 7 show you how you can take various interesting Lie groups and represent them as particular matrices that multiply column vectors of a particular type. And what's really cool is the formulas, yeah, I mean, some are obvious, like GLN is its own matrix realization, like it's the natural realization of itself. But there's other ones that are kind of like quirky and surprising, especially like the semi-direct stuff. There's some neat formulas at the end of Chapter 7. Make sure you read it, and maybe we'll come back to it. Anyway, so today, vector fields, Chapter 8 in John Lee's book. All right, so I'm going to try to do a lot today. We'll see what I get done, but I'll try. All right, so start with definition. Vector field on M is a section of the map pi, which is going from the tangent bundle of M to M. Written section map. In particular, the vector field itself, X, is a mapping from M to Tm, written P maps to X sub P typically. We use a sub P for the, that's the notation anyway. And so to say it's a section means the following. It just means that pi composed with X is equal to the identity on M. And really getting to the point that matters is that XP is an element of the tangent space at P to the M. Now that's probably the part that will make the most sense to you guys at the moment. But so if I was to draw a picture, you know, if this is the tangent bundle to M, and here's M, then pi goes like this. Remember, the definition of pi is it takes in a pair p comma v, and it just spits back out p. And essentially, a vector field is a mapping that goes the other way, all right? And to each point p, it attaches up here a p comma v, all right? Where v is, you know, well, I mean, the notation that I'm specifically using is p comma x of p, all right? So the x sub p is itself a derivation. It's an element of the tangent space of p. Let me just be less formal. A vector field on a manifold is simply an assignment at each point on the manifold of a vector, all right? And we can talk about a continuous vector field. That would mean that the assignment, you know, p maps to x of p is continuous. Or you could talk about a smooth vector field. All right, a smooth vector field would be a smooth assignment. It would make this mapping x a smooth map. That makes sense because this is a manifold, that's a manifold. So we have a definition of smooth making x smooth. Now, for, get out of my way. Let's see here, for p in the manifold M and, you know, chart, let's say u xi at p, we can write x sub p as equal to, and so he's been suppressing, Lee suppresses the summations. He's trying to be a good physicsy mathematician and imply his sums, but I'm going to be less adventurous and just write them, as I don't want to inadvertently confuse you guys. And I know, because I know that the repeated summation notation, it takes some getting used to. But that is the formula for a vector field on U, all right? So we can talk about a vector field on M. We can also talk about a vector field on a subset of M, right? So this would be a vector field on U. And here, the components, x sub I, u to r, these are these so-called component functions. Component functions of x, all right? Now, there's a proposition, proposition 8.1 says x smooth, let's say smooth on U, if and only if x sub I smooth for all I. Let's say, by the way, for the remainder of this lecture, the dimension of M, we're just going to be equal to n. All right. I know sometimes I make it equal to m, but I'll do n as in nanu nanu. So in short, to judge the smoothness of a vector field, it's smooth if and only if its component functions are themselves smooth. All right. And we'd like a notation for the set of all smooth vector fields. The set of all smooth vector fields on the manifold we'll use this symbol for. Funny looking, whatever, I don't know what this thing is, but what I can tell you this is that this is the set of all smooth vector fields on M, all right? Now, if you can talk about smooth vector fields on the whole of the manifold, we can also, yeah?
What is that character?
It's the set of all smooth vector fields on M.
I don't know, what is the character?
It's the set of all smooth vector fields on M. That's my best, that's the best I can do. I mean, I don't know what it is.
All right.
You look in it's there. I'm just making it up.
I just want to know what it's called.
And it's not just John Lee. I've seen this symbol before in other books. Like this is, whatever this thing is, it is what it is. What it is it's a letter we're not using anywhere else, so it's a great symbol, yeah.
The definition of a vector field is that xp can be any vector in the tangent space.
Oh.
So big xp can be
Yeah, so the thing is, in principle, right, if you think about the totality of all possible functions from M to the tangent bundle, right, you could look at all kinds of weirdo functions that maybe take, you could imagine another function that takes this P, right, and instead of mapping like to there, like I want it to, maybe it's not a vector field. Maybe instead of assigning there, it goes over here, And then, then that wouldn't be a vector field. It has to assign a vector at the point, right? It has to, the map, P has to map into the inverse image under pi. Like the inverse image of pi of the point P is, it's at least diffeomorphic to, the set P Cartesian product with TPM. I think it might actually be equal to that here. I forget our formalism, but yeah. But yeah, the vector field has to assign vectors at the point. It can't. It can't assign vector. It can't. You can't give in one point and stick a vector somewhere else like that. That wouldn't be a vector field. I don't know what that'd be, but it wouldn't be a vector field. And so this notation, this idea of section is an idea we'll see again in this course as we go on. Essentially, if you want to define a field of something, all right, so here's the story that we repeat in this course several times. At a point, we'll define how to make a particular kind of object, like we've done vectors. We've talked about how to make a vector at a point, right? To assign vectors at more than one point in a coherent fashion, what we do is we take a section of the bundle of that object, which in this case is the tangent bundle. So a section of the tangent bundle gives you a tangent vector at each point. Later, we'll talk about something called the cotangent bundle, which is like the disjoint union of all the cotangent spaces. And if we take a section of that bundle, it will give us a covector field, which we would call also a differential one form. There are also bundles where you take like all of the possible tensors of a higher type at each point. And that gives you like a tensor bundle. If you take a section of the tensor bundle, that gives you a tensor field. So a section of the bundle gives you a field. A field is really just an assignment of one of those objects at each point in the manifold in a smooth fashion. That's the bigger idea of what we're doing. But that's not in chapter 8. That's just, those ideas are collected in a number of future chapters, some of which I'm skipping. Oops. So, all right, let me get to the point here. So you can talk about a vector field on M. We can talk about like a vector field on just a subset of M, right? We can also talk about a vector field on a closed subset of M. You can talk about a vector field along a curve, right? A vector field along a curve is an assignment of a vector at each point along the curve, all right? And we can talk about smoothness of any of these kinds of vectors. Now, if you're talking about smoothness of a vector field along a closed subset, you can characterize that smoothness by the existence of an extension of the vector field past the closed subset, a neighborhood of the closed subset, which, the extension of the vector field is smooth in the sense we've already talked about. It's the usual story. If we want to talk about the smoothness of a map on a closed set, we talk about smoothness of an extension of the map on an open set that surrounds the closed set, and then that makes the mapping smooth on the closed subset. Same thing for vector fields as for anything else. And so yeah, some examples of vector fields. Now, actually, let me just go ahead and do my evil all at once. And it's not evil. What am I talking about? It's good stuff. So we can also talk, once you have vectors, of course, you can talk about linear independence of vectors, right? So like, okay, fine. I'm debating whether or not I should. Let me just do it. So if we have, so definition, oh, by the way, I guess I should probably say this before I write this. So I don't know what this thing is. Whatever this thing is, the set of vector fields, what can you tell me is that this is in fact a vector space. So this is actually a vector space. I should probably mention that before I talk about linear independence, because to talk about linear independence, we do need, some kind of vector space structure. So that's vector space. What's the addition? Like if I have x and y in vector fields, smooth vector fields, and a and l and b and r. Yeah, what's ax plus by defined to be at the point P? So axp plus byp, right? For all p and m. So yeah, the pointwise addition of vector fields, in this sense, gives it the structure of a vector space. There's also a 0 because we can just take the 0 vector field, right? Just assign the 0 vector at each point. That gives you the 0 vector for this space. But there's something a little bit more here that's interesting. So yeah, we got this vector space structure, but it's also a module over C infinity m. Now C infinity m, remember, is the set of, so the module structure I'm talking about here is we can take a smooth function times a vector field, all right? And if we take a smooth function times a vector field, we still get a vector field, all right? And the way that's done is very simple. We just do f of p times xp. So that's how we can multiply. That's the module action, if you will. So if you guys don't know what a module is, of course, right? All right, so you guys talk about vector space. A vector space is what you can add. You can add vectors in your vector space, right? And it satisfies certain axioms that if you've had group theory, that makes it a abelian group under addition. But then you also have these intertwining relations for your scalar multiplication. What kind of scalars do we multiply? For a vector space, we multiply by field scalars, right? So characteristic of the kind of vector space you're talking about, it'd be a real vector space, you have real scalars, or a complex vector space, you have complex scalars, or a finite field F vector space, you have finite field F scalars, right? And that scalar multiplication has to intertwine with the vector addition according to the axioms of the vector space, right? What a module is the same thing, give or take, except instead of having scalar multiplication by a field, you have scalar multiplication by a ring. All right, so the scalar multiplication, so this is a ring. What's a ring? A ring is a set which allows addition and multiplication, all right? Like the integers are a ring. So it's addition, multiplication, but maybe not inverses. So if you think about smooth functions, if you add two of them together, you get a smooth function. If you multiply two smooth functions together, oh man, I've been on the center board. Dang it. If you multiply smooth functions together, oh well, nothing the people on the internet don't already know. As I always tell them, they get what they pay for. So, and I haven't monetized my channel yet either. So, should I start like a subscription service? Like, you can watch the videos like a week before everybody else if you're a subscriber. Give a free. I give a free subscription to all my actual students.
So all vector spaces are modules over R.
All vector spaces are modules over R is true because their field is a ring. Right. Every vector space is itself a module in a sense. But so this is a ring. Smooth functions are a ring because if you multiply two smooth functions, you get a smooth function. If you add two smooth functions, you get a smooth function. There is a 0, right? There's a 0 in the smooth functions. There's also an identity. If you just define the constant function 1, that gives you something, that function times any other function gives you back 1. However, there are lots of things which are non-zero and yet don't have inverses. The bump functions, principal among them. So you have a bump function. you have a function which is non-zero on a certain subset, but 0 everywhere else. There's no way you can multiply that thing by another function and get back the constant function 1, which serves as the multiplicative identity. So there's like infinitely many what are called zero divisors in this ring I'm describing. It's not a field, but it does have many of the nice properties of the field, the smooth set of smooth functions. And so that is why the set of vector fields, with respect to multiplication by functions, is not a vector space. It is technically a module in that sense. But of course, if we just talk about scalar multiplication by numbers, it is a vector space. It's still true that the sum of two vector fields is a vector field. And if I take a scalar multiple of a vector field by, a number, I do get a vector. So it is closed under real scalar multiplication. It's a real vector space, but it also has this additional and far more deep structure of being a module with respect to the smooth functions. So that's what that's about. Now, you'll study modules in like Math 422, maybe. But anyway, modules, doing vector space stuff over a ring, it does have certain, it's more complicated, but it's worth it. Anyway, so now that we've got that definition, if you have x1 xk a k-tuple of vector fields on some subset, let's say, of a manifold M, then this k-tuple is linearly independent. It's linearly independent if you look at if you look at that k-tuple at any point, right? If you just feed these k vector fields, right? Feed these k vector fields a point is linearly independent subset of TPM for all P and A. Let me try to put that in words. A set of vector fields is linearly independent only if, whenever we look at any point in the domain of consideration, that set of vector fields gives us a set of vectors at that point which is linearly independent. So this is what we mean by linear independence of a set of vector fields. So it's basically, if the set of vector fields is linearly independent, that means that if you just pick a point, then all of those vectors that the vector fields are giving you at that point give you linear independence at that point. So it's like, in some sense, you could say pointwise linear independence. And if x1 p xk p span TPM for each P in A, then this k-tuple spans how to say that? Sorry. Not sure the exact language here. Well, well, it said this spans the tangent bundle. I probably would say over A. I'm not sure that's the language that John Lee used, but all right. All right. So, yeah, what is it?
You just said it's said to span the tangent bundle.
Said the span of the tangent bundle, yeah. See, the thing I think about is to span the, all right, fine, but I would say that like the whole, it doesn't give you the whole tangent bundle because A is a subset, you know? So I think that language is, it's okay, it's a span inside the tangent bundle, sure. I would see it as spanning the tangent bundle over A. You know, TA, if you take TA as the disjoint union of the tangent spaces to A, making some of the usual identifications perhaps. Okay, anyway, that said, if we have x1, well, excuse me, language here. One sec. Where was I? Where did I put that thing? Oh, here it is. So I'd like to introduce the terms, like the term frame. What's a frame? So a local frame on U, all right, a subset of M, is linearly independent spanning set of vector fields E1 EK on U. Now, I mean, truth be told, of course, if M is n-dimensional and that U is I guess the question is, all right, fine. So if U is an open subset of M, right, then certainly I can tell you what's going to happen. We need n of them to span, because U is n-dimensional submanifold of M. So, but I'll leave it as K because that's what he has. So linear independent set of vector fields E1 through EK. On U. Okay, so in short, a local frame is a linearly independent spanning set on some subset of the manifold. A global frame is, guess what? Yeah, it is a frame on M, right? And I'd actually, well, anyway, I'm tempted to extend the use of, well, I guess I shouldn't though. All right, so some examples. So example 1, if we think about M equals to Rn, and let's use the coordinates U1, U2, UN for my Cartesian coordinates, not like John Lee, but like me, then if you look at like partial U1, partial U2, partial UN, that the coordinate derivations, right? This is the global coordinate frame. Global coordinate frame on Rn, right? In fact, this is the global Cartesian coordinate frame. If you want to, you can use the identification of this with the standard basis. The standard basis gives you a global frame. All right? Now, so that would be, let me call that example A. Example B, if you have U is a subset of M, a chart domain, so we have X is, usual U to Rn, right? So the chart is X. Then partial x1, partial x2, partial xn. This gives you the local coordinate frame, right? So again, a frame here is a collection of vector fields which serve to give you a basis at each point in the tangent space of the object under consideration. So you could talk about like in principle, you could talk about a framing of a curve or something, you know, or a submanifold, but I guess he's not quite going there yet. So here's another one we haven't quite talked about yet, but dd theta is a global frame for S1. And D, partial theta 1, partial theta 2, partial theta n is global frame for the n torus. Now, I should be careful. Neither of these are global coordinate frames. Now, this is fussy, all right? Neither of C or D are global coordinate frames. The reason being that we can't, as much as I'd love to, I mean, this is the pain of complex analysis, right? That you can't use a single angle chart for the whole circle. That 2 pi jump is an inevitability, which forbids us from saying that the whole circle is covered by one angle coordinate. We cannot escape the failure of injectivity at that angle jump, right? But the thing is, if you think about two different choices of angle, right? If you talk about angle theta tilde and angle theta, what's the difference? Well, the relation between those two is just addition by some 2 pi multiple, right? I mean, I guess you could define angle more weirdly than that, but like the usual argument choices are like this. Anyway, the point is that if we're at a point on the circle where they're both the angle functions are defined, if we look then at the coordinate frame that these derive, they would agree on their differentiation of functions on the circle, which is to say that you'd have partial theta tilde equals to partial theta on the points of their overlap. So like to picture it, the situation is something like this, right? Maybe you've got like theta is your coordinate map on that, right? And maybe the angle jump for theta tilde is over here, you know? Like that. So at every point on the circle, you either got a definition for theta tilde, or for both. And so if you think about this, you can extend either the coordinate derivation with respect to theta or the theta tilde, whichever one you like. Let's say theta. You can extend the coordinate derivation for theta to the whole circle in the obvious fashion, right? I was talking to Ernesto about this earlier, as it's kind of like these sort of artificial examples in Calculus 1, where you're doing something like you've got a function whose graph looks like this, you know? So slope 1, but right here, right, there's a jump, right? If this is y equals f of x, and this point right here is, whatever that is, let's say 3, then technically f prime of 3, does not exist, right? But if you were to take, say, f prime of x, what do you have? You have f prime of x is equal to, well, 1, it's equal to 1 for x not equal to 3, So how do you continuously extend the derivative? You just define the extension of the derivative to be 1 at the place where it's undefined. Now it's no longer the derivative of the function at that point, but it is nevertheless a continuous extension of the derivative. In the same sense, we can extend the coordinate derivation with respect to the angle function to be a global frame. It's just not a coordinate frame. Does that make sense? And I can give you like stone cold formulas for it. Like partial theta is just literally, minus sine t partial, I'm going to use x, minus y partial x plus x partial y. I'm pretty sure that is literally what partial theta is on the unit circle. That's what that coordinate frame looks like in Cartesians. Same story for the N torus, right? It is also that global frame for each one of the angle coordinates, right? And again, those coordinates can only be defined on most of the circles that comprise Tn, right? You guys remember what Tn is, right? The torus, it's S1 cross S1 cross cross Sn, n-fold times. And so basically, you're using theta 1 for this one, theta 2 for that one, theta n for the nth one. Because a typical point in Tn looks like e to the I theta 1, e to the I theta n, right? So that if you know your choice of angles, then you've uniquely defined the point in the N torus. So we have a natural angle coordinate map chart on the N torus. All right. What else can I tell you guys? Well, let's see here. You can also talk about what do you think it would mean if we said that the frame was orthonormal? What would it mean for a frame to be orthonormal? Vectors are length 1, right? So like definition, frame on Rn, or a subset, I should say a subset of Rn is orthonormal. So, and the frame I'm talking about is, as usual, E1 ek, let's say. It's orthonormal if you have E1 at P ek at P orthonormal subset of TP Rn, which of course we identify with Rn in this context. And in that sense, you can take the dot product of vectors. How would you do it? You just, basically strip off the components and think of them as just plain old geometric vectors. That's an orthonormal frame. So like we'd have this formula for an orthonormal frame. If you were to take, say, EI at P dotted with EJ at P, you would get Kronecker delta IJ for all P and A. And so you might as well just say that we have the vector field I dotted with the vector field J is equal to Kronecker delta IJ on A. You could say that. Now, John Lee doesn't say these things, but I think you could say these things reasonably. An orthonormal frame of Rn has this. Now, you understand how I'm defining the dot product. Let me be a little bit less vague. So, like for example, let me just be really, really concrete about this. So if I had, let's say, E1 equal to, I don't know, cosine of x, partial x, plus sine of x, partial y, and I had E2 was, I don't know, minus sine of x, partial x, plus cosine of x, partial y, all right? Then I would understand E1 dot E1 to mean cosine of x, comma sine of x, dot product with itself, So that would give me give me 1 because sine squared plus cosine squared is 1. And likewise, if I was to calculate E2 with dot E2, well, I would again get, sine squared plus cosine squared, which would be 1. And you can also check this out. E1 dot E2 is, what is it? Well, it's, cosine x times minus sine x plus sine x cosine x, also known as 0. So E1 and E2 are an example of an orthonormal frame on R2. All right? It's a kind of weird orthonormal frame too, isn't it? You notice I just put the x function in there. Think about this. You could do the same game and replace x with like some kind of wacky. You could put so many different things. Yeah? What? Oh, that is only for the set of vector fields. I'm sorry. I will not allow that to appear anywhere else. It is its only job is to communicate, hey, set of vector fields. Yeah, it would be like using pi as a variable. It would just be wrong.
We use pi as a map.
Is it as a map? Oh, dang it. Such a hypocrite. You're right. But I mean, a map is totally different than a variable. So.
You definitely can't use E for anything else, right?
Okay, so are we clear? So you understand how I have brought the dot product onto the scene here? So we only really have a dot product in the natural sense of the manifold at the moment for like a subset of Rn. To get the concept of dot product for an arbitrary geometric manifold, we'll need to introduce something else called the metric. We haven't done that yet. And to do that is to start talking about Riemannian geometry, which we haven't gotten to yet. All right. So that's orthonormality. And so, yeah, I guess one other example here, example 3, another nice example, you could do like this. E1 is equal to x partial x plus y partial y. My bad, that was supposed to be x over r and y over r. And then E2 is like minus y over r partial x plus x over r partial y. And you can again check with respect to the dot product that we just introduced, like E1 dot E1 is actually equal to x squared plus y squared over r squared, which is x squared plus y squared over x squared plus y squared, because r here means the square root of x squared plus y squared. So that's 1. Let me say that. R, by definition, square root of x squared plus y squared for this example. And likewise, very similarly, E2 dot E2 is also equal to 1. And you can easily see that E1 dot E2 is what? Minus xy plus xy over r squared, which is 0. So what do you guys think? Is this an orthonormal frame on R2? So this one up here was orthonormal. This guy is here. These are orthonormal frame on what? R2, right? Agree? You're like, it seems like a trap. Yeah? I hope it feels like a trap, because it's a trap. What's the fine print here? What happens, r equals to 0, we're in a world of hurt, right? So this is actually orthonormal frame on the punctured plane. Can you guys tell me, in the language of my calculus 3 stuff, I don't know if you guys know or not. I guess you guys haven't had Calc 3 with me, have you? So why would you know? But
I had Calc 3 with you for 1 day.
for 1 day. How dare you, sir? Let's see here. So
I have been with Jeff for like a few months.
in my Calculus 3 notes, my notation is that E1 is what I would call R hat, and E2 of this example is what I would call theta hat. They are the unit vector fields that point in the direction of increasing radius or increasing standard angle in the usual counterclockwise fashion. That's what these are. If you write them in terms of polar coordinates, R hat is literally in the usual notation cos theta, sine theta, and theta hat in the usual notation is minus sine theta, cosine theta. Those are manifestly unit vector fields, and they're also manifestly perpendicular. And to get one from the other, you just rotate by 90 degrees. That's what you do. And yeah, I mean, you can just picture those. They point, the R hat points radially out from the origin, and theta hat wraps around it. It is the tangent vector field to circles concentric about the origin. So I refer to these in my Calculus 3 notes, I call these the polar coordinate frame. So if you take my Calculus 3, I talk about frames. Frames are important. So to me, a frame is the natural completion of the discussion of coordinate system. Like coordinate system gives you a one-to-one correspondence between points. The frame then tells you how to build natural basis for the vector fields corresponding to those coordinates at a point. So to me, the frame of a coordinate system is like a set of vectors which are unit vectors which point in the direction of increasing coordinates of that coordinate system. You can derive those in terms of Calculus 3 by taking the gradient of your coordinate functions and then normalizing them by dividing by the magnitude of the gradient. There's a straightforward procedure that we can use to calculate the coordinate frame for a given abstract coordinate system. Also, there's a theorem here in Lee where he tells you that if you've got a frame, not necessarily orthonormal frame, just a smooth frame on a subset of Rn, then you can apply the Gram-Schmidt algorithm to it, and you can convert it to a smooth orthonormal frame. The way you do this is you take your first vector, you basically just divide by the magnitude of the vector, and if you normalize, that normalizes the vector to length 1. Then you take your second vector field, and at each point, you subtract off the part of that vector field which is parallel to the first vector. The remaining vector, you then normalize. That gives you a vector which is length 1 and perpendicular to your first vector. And then you just keep repeating this process, each time subtracting off the part which is projected into the shadow of the original directions. And then you normalize to length 1. This is the Gram-Schmidt algorithm. And you just have to do it at each point rather than, I mean, we usually, in linear algebra, you talk about this for a static set of vectors, but now we're doing it for vector fields, which means we have to apply the Gram-Schmidt algorithm point-wise. So, but that's actually not as bad as it sounds. Like if you actually had coordinate functions, you could actually carry this out. It wouldn't be the most horrible thing. But I don't have an example for you, but I'm just saying you could do it. Okay, so moving along here. Definition: a manifold with or without boundary which admits a smooth global frame is said to be parallelizable. Blah. That's a mouthful. So definition: parallelizable, a smooth manifold with or without boundary which admits a global I forgot smooth global frame is parallelizable, which I'm going to abbreviate as this means, ultimately, this means that the tangent bundle, in fact, is diffeomorphic to M cross Rn. In other words, in the language of fiber bundles, a manifold is parallelizable if its tangent bundle is trivial. See, a trivial tangent bundle is one for which can be written as, more generally, a fiber bundle is trivial if it can be written as a simple Cartesian product. Usually, this is such a mess. Usually, a fiber bundle cannot be written as a Cartesian product, except locally. Like locally, a fiber bundle is a Cartesian product, but not globally such. There are local trivializing maps. There are local maps which put a fiber bundle in bijective correspondence with its defining Cartesian product, but you can't do it globally. So this ability to write the whole of the tangent bundle as a Cartesian product means that the tangent bundle is a so-called trivial bundle. There was a homework problem on this where you were asked to show that the tangent bundle to the circle was diffeomorphic to the circle cross R. That's this in action, because the diffeomorphism, the way you wrote it down, was to use the theta coordinate map, the theta frame, the smooth global theta, partial theta map, theta field. That is actually what allowed you to write the diffeomorphism from the tangent bundle to M. And the diffeomorphism was just this. So if you want like a diffeomorphism from the tangent bundle to the circle cross R, the mapping, I believe, is just this. So a typical point in here looks like e to the I theta, and then you've got your partial theta, right? At the point, let's put a knot there so we feel better about our life. So there's your typical point in the tangent bundle, and all you map to is theta naught. Oh my bad, e to the I theta naught. And my bad. So a typical thing here, it doesn't just look like a typical tangent vector. It's not just this, right? That's a special tangent vector. An arbitrary tangent vector to the circle at the point, if we're at the point theta naught, right? What does the tangent space look like there? I mean, geometrically, it's like this, right? So this guy, maybe you can visualize as partial theta at theta naught. It's a specific tangent vector, right? An arbitrary one is a scalar multiple of that. So a typical point in the tangent bundle to the circle would look like this. It's a scalar multiple of your coordinate derivation. But I don't want it just to be the coordinate derivation, right? I want to extend that, like we were talking about, to be the global angle, the global theta hat, which for stupid picky reasons is not a global coordinate frame, even though it is a global smooth frame. And so you just T. And that's a diffeomorphism. That's the diffeomorphism of the tangent bundle to the circle and S1 cross R. And essentially that same trick can be used to parallelize, well, to trivialize the tangent bundle for any M that has a global vector field, because you can just do the same, basically the same trick. If you take, you take your, you're going from the tangent space, tangent bundle to M cross Rn in that context, a larger context. And so essentially you just, take your point. Well, let me not write it down, but let me just talk about it. You take the point, comma, the vector, all right? But the vector you can express as a unique linear combination of your frame, your global frame. And so how do you obtain an Rn vector for the map? You simply strip those coordinates off. And that assignment is a smooth one because of the smoothness of the global frame. And as such, you have a diffeomorphism of M and M cross Rn. So here's that. But anyway, so this is parallelizable. And there are very, very interesting things to talk about here. So like example, where am I? Example 4, I suppose. So check this out, right? So example 4, what are parallelizable? Well, we already know. Rn, S1, Tn, all parallelizable, right? Why? Because we already had example 1. And we have the smooth global frame for Rn, for S1, and for Tn. They're all there, right? It turns out, and this is, I don't think this is obvious, but the 3 sphere and the 7 sphere are parallelizable. Now that's an exercise, I may or may not have assigned it. I don't know how hard those exercises are. That's dangerous. If I've assigned it, that's very dangerous for you and for me, since I've agreed to write solutions to these things. But here's the thing. In 1958, Bott and Milner, and separately Curvaire, showed that the circle, the 3 sphere, and the 7 sphere are the only spheres which are parallelizable. So these are the only parallelizable spheres. Again, this was Milner, Bott, and Curvaire, 1958. They independently, Bott and Milner are working together, and I think the other fellow there separately. They proved that the only spheres which are parallelizable are these guys. There's a beautiful theorem that we will soon prove. In fact, I can sketch the proof of it for you already because Lie groups are just that beautiful. So here's the theorem. Lie groups are parallelizable. So here's a sketch of the proof of that. So here's your Lie group, right? And here's your eins element. We can prove that there exists, I mean, well, it's just tangent space. There exists a basis for the tangent space, right? So you can take a basis for the tangent space, right? The tangent space at the eins element of G, all right? And then basically all you have to do is use the left multiplication maps. And because they're diffeomorphisms, you can transport this basis everywhere else. You just push it wherever you want it to go. And it will give you a smooth global frame on the Lie group. Now it's going to take me a half hour of class to build up the machinery I just talked about, but that's what happens. Lie groups are parallelizable. And it turns out that S1 and S3, so these guys, this one and this one, turns out that these have Lie group structure. In other words, you can realize them as a Lie group. And I think we've already talked about that actually in the homework, if you think about it. At least for S1. Like the Lie group structure of S1 is kind of obvious. E to the I theta 1 times e to the I theta 2 is e to the I theta 1 plus theta 2. That's the Lie group. Like it's just complex multiplications, the Lie group structure. And because S3 is a subset of C2 cross, is a subset of C2, right? S3 is a subset of R4, but we can view it as C2 cross C2. It's the set of ZW in C2 such that like the Z times Z bar plus W times W bar